Okay, so before we talk about exponential functions, let's do a few exponent question warm-up problems here, where we just kind of get used to working with exponents, and then we'll break it down, and I'll kind of tell you what may be new about this unit. So first of all, let's just go through a few of these. I'm not going to do every single one. Some of the properties are repeated, so we'll just skip the repeated ones. But it says use the properties of exponents to simplify the expression. So if you're, just for maybe a quick review, if you have something that looks like this, I don't know, it doesn't matter. Let's say a to the x. You have, well, the whole thing here, okay, the whole thing is a power. So when we refer to a power, we are referring to something that looks like that. And a power has two parts to it. This part is the exponent. So when you see a to the x, if you just say, oh, there's an exponent, well, yes, that's the little number up top, but it also has the number down here, which we call the base. And so together, a base and an exponent is referred to as a power. Okay, so when we use the properties of exponents, obviously it has to do with having a whole power here, because you don't just have an exponent hanging out in the middle of nowhere. It has to have a base to it. So coming down here, when you have a power times a power, or 5 to the 2x times 5 to the negative x, the property that you use here is that you add, okay, when they both have the same base, you add the exponents. So that's 5 to the 2x plus negative x, and that's just going to be 2x, and negative x is just x. You just subtract that x, so 5 to the x. So when you're multiplying powers with the same base, you just add their exponents. So in number 2, then, just to reaffirm that 3 times that and that, well, you just add their exponents, and that's going to give you 3 to the 2x. Okay. Just the opposite in numbers 3 and 4 is when you divide powers with the same base, you subtract their exponents. Sometimes you would say that these would just cancel, but technically you just subtract their exponents. So 5x minus 2x is going to be 4 to the 3x. Okay. Those are the most commonly used properties right there, and we're not doing every single property, but those are probably the most common. If you look at number 5 here, 5 is technically this, so you don't have to do this. We have a much shorter way of writing it, but 4x squared is technically 4x times 4x. 4 to the x, sorry, times 4 to the x. Just put that the wrong way. So when you have that, you would have 4 to the x plus x, which is just going to be 4 to the 2x, which is the long way of the shortcut, which would have just said that when you have an exponent outside of the parentheses, when you're raising a power to an exponent, you just multiply the two. So a shorter way would have been just to take 4 to the x and the exponents multiply, and you get 2x. So we'll do that down here. So instead of writing out 4 to the 2x 5 times, you can just say that it's going to be 4 to the 10x, which is way faster. So when you're multiplying with a base, two powers with a base, you add the exponents. But when you have an exponent outside, then you just multiply through. And you don't raise it to any other level. There's no higher level than this. So when you say you raise an exponent to an exponent, you're not really raising that any farther up. That's as high as it goes. So keep it right there on that level. Okay, number 7, when you have a negative exponent. Negative exponent. Well, for the first, well, you can do this a couple ways, but for maybe the first rule is that an exponent outside of parentheses comes in and needs to hit every term inside the parentheses. So it needs to multiply the exponent up here in the numerator, and it needs to multiply the exponent in the denominator. So it's 2 to the negative x over 3 to the negative x. So it hits numerator and denominator. That would be the first property. Second property then is, what do you do with a negative exponent? Because that is not something that will ever leave as an answer. It's a negative exponent. Do you remember what that does? A negative exponent doesn't mean it's a negative number. It just means that you need to take that term, the power with the negative exponent, to the other side of the fraction bar. So we're going to do it twice here. The 2 to the negative x moves down below as 2 to the positive x, and 3 to the negative x moves up as 3 to the positive x. And then that's it. Those do not have the same base, so you can't do anything with them. You can't cancel them or anything. You just have to keep them like that. Okay, skipping number 8. Maybe something like number 2 or number 9 here with 2 to the 3x. So again, we multiply in, just multiply like normal. That's going to give me 2. When we multiply those together, 3x times negative a third just gives me negative 1x or negative x. And that's just waiting for the property that says you take this to the other side of the fraction, which means it needs to go down below the fraction symbol, and then that would stay up. Okay. Number 10 we'll do just because we can do the actual calculation here. 16 to the x to the 1/4, that could be 16 to the 1/4 x, or x over 4. And technically what we can do here, and this might be a little bit more advanced, but we're going to keep the 16 to the 1/4 in, and we're going to swap the x out here. Watch that little trick. Because you're just multiplying those two, so it really doesn't matter what the order is. 16 to the 1/4. It might be complicated for you, but do you remember how to do what they're called rational exponents? Something to the 1/4. I don't know if you remember this or not. But the 1/4 is taking the 4th root of 16. I don't know if you remember that or not. Anybody remember doing that? Fractions as exponents are like roots. 1/4. Anyway, 16, the 4th root of 16 is 2. This just comes out as 2x. We're not going to go too deeply into roots in this chapter, even though we certainly could. We're not. We're just going to kind of stick with the exponent. So don't stress about that one right there. It's a little bit maybe too complicated. All right. Anyway, so what is then an exponential function? Those are all powers with exponents, but you're usually not probably familiar with putting x's up there. When you've done exponent rules in the past, you've done them like this: x to the 2 times x to the 3, and that's the same rule that we were doing here, and that would be x to the 5. That's what you're used to. You're used to putting the variable down here and the exponent up, or the number being up here. Well, an exponential function is the reverse, and that's what we were doing with all of these. You have the variable up here, and your base is actually a number. So, like you see right here in this box, an exponential function is one like this, where your number down here, the base is a number, and your variable is up here in the exponent. So we're going to do a little bit more than this. I'm going to kind of give you a little bit of a more general form, but this would be called your parent exponential function. This is, if somebody says exponential function, or growing exponentially, or something with the word exponential. Morning. Yep. Then that's what should come to mind. Exponentially means that it goes up like this. Okay, but there can be variations on that, of course, and just like there's variations on the conics where they shifted and switched up and down and all that stuff. What do we do first chapter? Quadratics, and how you shift your parabola and you can move it up and down. That general form, okay, so I'm going to kind of give you a, I don't know where the white space is here that I want to use. We'll just say the general form is going to be this. Y equals, and then what did they use there? We'll use A times B to the x plus k. So that should take care of pretty much all the different variations that you're going to get. I'm going to kind of throw some stuff in here though, if I can. The A, okay, the A, we'll just say it can be one of two things. It's positive or negative. What the actual number there, I mean, yeah, it's going to make a difference, but whether it's positive or negative, it's going to make your graph either open up or open down. Just like positive and negative A's have done with practically every graph that you've done in your life. A positive number out here goes up, negative is going to make it go down. Kind of the more interesting one though here is this B, this base B, because there are two categories here. For one, it's always going to be positive. Okay, B is always going to be positive. It's never going to be negative. If B was ever negative, if you ever looked at this and you saw negative 5 to the something, that negative is actually the A. It's not the B. Okay, the B is always positive. Anything negative would just be considered the A. So if that's positive, there's really two different distinctions here. I don't know if I'm going to be able to fit it in here or not. I'll try. You can either be between 0 and 1, or you can be greater than 1. Okay, so you can either be a fraction, but when I say fraction, I mean something like a half, a third, a fourth, 2/5, not something like 5 halves. Because 5 halves, it's a fraction, but it's greater than 1. So when we say a fraction, we mean a fraction between 0 and 1. Like a half is a perfect one to use. When it's like that, your exponential function, it doesn't look like this. This one is right here. When your b is greater than 1, that's what it looks like. When your b is between 0 and 1, it reverses. And let me draw you a quick little graph like this. So if we use the same colors, it does this. It is kind of flipped. I don't know what you would say. It's flipped around the y-axis. So this one is that. When you have a fraction as your base, then your graph goes down. Okay, and we'll kind of explain that here in a couple minutes. But when your base is greater than 1, it goes up. When your b is 1, then it's 1 to the x, but 1 to the anything, no matter what your number up here, is always 1. So it's really not even an exponential, it's just a flat line. So we exclude 1 as ever being our base, because then it's not even. It doesn't do anything, it just stays flat. Okay, and then the k is the vertical, I don't want to say change, but vertical shift. Just like our k has always been. So it's the vertical shift, and you might want to call this also it's the horizontal asymptotes. That's a funny word, but asymptote. You ever heard feds yell, "Holy shift"? Did you hear that the other day? Somebody was in, I don't know if you heard it. But there's a funny math saying that says, I need to get it right, or else. It's something like, it's like, holy shift, look at the asymptote on that mother function. She'll yell that, and it sounds funny because she yells it very intensely, but that's kind of, you can kind of get the idea there. But the asymptote shifts the graph. I have to say it slow because I'll stop saying it. But anyway, it shifts the graph. In this case, it's going to shift it up and down. Okay, so let's explore this a little bit before we do some graphing. Tomorrow we will do solving exponential equations, as well as doing some application problems, which I find very interesting, and I'm sure you will. find them interesting as well when we talk about decay and, I don't know, appreciation and stuff. Anyway, so let's just take a real quick thing here and look at this. If you compare things that you're familiar with, a linear function, a quadratic function versus an exponential function. Let's do it two ways here. Let's look at a little chart, an XY chart, and then we'll see what the graph of it looks like. Let's go with a few numbers here like -1, 0, 1, 2, 3, 4, 5, 6 was the chosen amount. Let's see if I can fit that in for all of these. How many lines is that? 1, 2, 3, 4, 5, 6, 7 lines. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Bless you. -1, 0, 1, 2, 3, 4, 5, 6. 6. Good old-fashioned, old-school plotting here, and then we'll sketch a little graph of it, just so that you can kind of see what these are, how these are related or not related. Okay, so let's fill those out. This is really just a plugging in, not going to be very hard at all. But when you plug in, these are all your x's. Okay, this is the x column and then the y. I should put that on there. But when your x is -1, that's going to give you -2, and then 0, 2, 4, 6, 8, 10, 12. And graphing y equals 2x, so you know you go through 0, 0, that's right on there. But then it's just going to be, and again, this is not really very good, it's just going up like that. So what you see with a linear function, okay, what you see with a linear function, and this has to do with the idea of slope, to be honest, but in a linear function, every movement, either direction, left or right, is you increase your y in the exact same amount. So for every increase in x, you are increasing at a constant amount in your y. You can see that you're jumping 2. Right? You notice that? Okay. Constant change is a linear function. You're increasing at a constant rate. That is called slope, okay? But that is what a linear function does. Every movement over here is a constant. It's not that it's just predictable, but it's a constant number. That's what a linear function does. Okay, let's do a quadratic. -1 is 1, 0, 1, and now we're squaring all of these. That's all I'm doing. 2 squared is 4, 9, 16, 25, 36, etc. So what does a quadratic look like? Well, it's just your normal looking quadratic. And again, we're not plotting necessarily here, we're just doing that. So then when we kind of look at our numbers here, every movement to the right, we are increasing, okay, not at a constant amount. You can't say that you're adding the same number to the one before it. You are getting bigger faster though. You can just look at the 6. In a linear, you only got up to 12, versus a quadratic, you got up to 36. We are increasing at a faster rate, but it could be predictable. You know, you can see that you're increasing by 1, 3, 5, 7, 9, 11. You're actually increasing by kind of the odds. You just keep going up more and more and more by the odds. So we're definitely increasing faster than the linear function, but let's throw the exponential function in and see how that compares. Plugging a -1 in here, it's a little bit trickier because you have 2 to the -1, which is, think about 2 to the -1 for a second. The rules of exponents say that that doesn't make a negative number. It just means that this goes down to the denominator, so it's a half. Negative exponents typically mean smaller numbers, not negative numbers. Smaller, but doesn't cross 0. 0, anything to the 0 is 1, and then 2 to the 1 is 2. Let's see how far we can get here. 2 to the 2 is 4. 2 to the 3 is 8. 2 to the 4 is 16. So what's the pattern? What are we doing here? Just multiplying our previous number by the base. We're multiplying the previous number, in this case, by 2. And that's what an exponential function does. It multiplies the previous number in the sequence by whatever the base is. So what does this look like? It looks like that one that's up there above us. Never goes down below 0. It never turns negative, no matter how small you make that exponent. You never can change it to be a negative number. It just gets closer and closer and closer to 0. But it shoots up even faster. You can see even when we get to the 6, so that it kind of stays close there for a while, but then once it passes 5, then it gets bigger and bigger and bigger pretty fast. And that's kind of the idea of an exponential increase. If somebody says it increases exponentially, they basically just mean that it is increasing fast. Okay, it might start low, but then once it starts shooting up, it really goes up there pretty fast. Okay, let's graph a couple of these and then throw in the second page here, the third page, but let's just do a couple basic graphs. Okay, graph 4 to the x plus 2, state the domain and the range. Alright, so when I look at this, it's important that you be able to recognize a couple things. One, this is the exponential part. I'll just call that the exponential part. And this then is your vertical change or your horizontal, I'll write it in capital letters. This right there is your horizontal asymptote. Because when you go to graph this, it's more important to set up your asymptotes first. Your hyperbolas had asymptotes, and you drew those diagonals through the boxes so that you had like a scaffold, a frame to draw your hyperbola. Same thing with exponentials. Okay, it's with a lot of functions. If you draw the asymptotes first, then it helps you. So the horizontal asymptote at 2, that's this number here. You go over here to 2, and you draw a dotted line at 2. Okay, the next thing that I see is that the a value here, what would you call the a value? If this matches, this should match this general form. Remember, a times b to the x plus or minus k. So we already said that the k was positive 2. 4 to the x is the b, so what's the a? It's not complicated. It's just 1, right? If you had to throw something in the front of there, it'd be a 1. So it's positive, so I know that this graph is going to open up. And I say that because that answers for me a little bit of this over here. It answers for me the range question. Because the domain question, that's going to be a nice one. Because every single question in this chapter, every single exponential function, the domain is all real numbers. And we kind of write that with a little symbol that looks like that. It looks like 2 lines in front of the R. You could say all real numbers. There's nothing wrong with that. But it's like an R with 2 front lines there. All real numbers. Okay, which means that when you have an equation that I don't know, if you put into your calculator 2 and then you use the little exponent button, you could put in any real number that you could think of and you would get an answer. You can't break that. 2 to the any real number. Negative 1,000,000, positive 1,000,000, 0, a half, square root of 39. Doesn't matter. You're going to get something out of your calculator. Okay, so what that means is any x, because this is your x variable, any x that you can think of, as long as it's a real number, it's not like 2i, that doesn't count, that's going to break it, it'll work. So the domain on all of our exponential functions is all real numbers. The range, though, is not all real numbers, okay, because the range are, well, what are the y values that come out of your function? If I plug in a number, what can I expect to come out? Okay, that's what the range is telling you. And the range depends on your horizontal asymptote. So for this, I can see that I'm not going to go past my asymptote, and I'm not going to go below it because I know that my exponential function goes up, it's positive. So I'm not going to do anything down here. So my range is going to be y's greater than 2. All y's greater than 2. It's not going to touch 2, it's going to be greater than 2. What it actually looks like, that's where the chart comes in, and I'm going to plot some points and connect the dots. So -1, if I plug in -1, and this is something that you can use a calculator for. You're probably going to have a calculator out every single lesson here in this chapter at some point. So we might not need it yet. 4 to the -1 is negative, or is 1/4 plus 2, so it's 2.25, 2 1/4. You could probably do that without calculator. 0 goes in there. Anything to the 0 is 1, so 1 plus 2 is 3. So 0, 3. 1, so 4 to the 1 is 4, plus 2 is 6. I can do that one. 1, 2, 3, 4, 5, 6. Highly unlikely that I'm going to get any more than that. Yeah, 4 squared is 16, plus 2 is 18. That's out of the range. Or that's out of my, out of my box. If I threw one more on there, like -2, let's take it to the left one more. -2, 4 to the -2 is 1 over 4 to the 2, which is 1 over 16. So 2 and 1/16, whatever that decimal is, it's 2.125. So that's really kind of not much better there. But that's what we should be expecting. Remember, think about what our exponential function should look like. It's going to be this. If our base is greater than 1, which it is, it's 4, then this is what we expect. Flat up. But there was a shift. There was a shift of 2 up. So that this flat part goes right there, and then it shoots up like that. In an exponential function, the previous number should be kind of, if you were to take 2 away from this, if you take 2 away, it's 16. You take 2 away, it's 4. You take 2 away, it's 1. 1, 4, 16. The next number is 4 times as big as the previous one. But then we had to add 2 on it. So, it doesn't really look like it's 4 times, but it would be 1, and then it was a 4, and then it was a 16. And then we added 2. So the base tells you kind of how fast you're going to shoot up there. All right, let's try a couple more here from this page. Let's make number 2. I know it's not. Let's do number 2, but let's throw a negative onto this. Negative. So number 2 back here. Let me include a negative sign there where there wasn't. Okay, so let's do that one. So when I look at this with the negative, first thing I see that there is no extra term here. There's no k, which means that my horizontal asymptote is where it's standard, where it usually lives, its standard place, which is at 0. So the range here, for the domain, it's all real numbers. For the range, it's y is greater than 0. For actually what it looks like, it's kind of a bad one here because I changed it to negative, and there's not a lot of room down here because I'm going to need to go down there. Maybe we'll do it right here. I'm going to do a vertical chart. The rule here is that you just take a splattering of x's all the way across, because if your domain is all real numbers, it's not like you're going to pick an x and it's not going to work. It's going to work. The question, though, is it going to be graphable? Is the number that you get when you plug in your x going to be something that you can graph on this grid? And that is not always the case. So, like if you went all the way over here and picked -1, 2, 3, 4, if you picked -5, or if you picked 1, 2, 3, 4, 5, +5, there's a chance that one or both of those ends are not going to be graphable. Probably the bigger end here, because it's just going to be way off into way down here or way up. In this case, because it's negative, it's going to be way down here. Oh, this is wrong because I made it negative. You're going below that. I should have. This is a negative a, so that means that you're going to be going down, and you're going to be below that y is equal to 0 line. So taking a splattering across there, I'm not actually going to do the -5 and the +5. Those are kind of at the extremes. I'm going to do something like -3, -1, 0. I don't know how many you need to do here. I would say at least 4. Oh, I don't know. Let's say 2. Spread it out a little bit. So -1/3 to the 3, and then the exponent -3. That's getting a little bit complicated for your head. You probably could, but why not use the calculator? That's all I'm going to do right here. I'm going to go -1/3 times 3, and then the exponent for the first one is -3. -0.01. Very small. So -3, 1, 2, 3. You're basically at 0. I mean, you can't really make your dot any closer than that. Then we're going to do that, but we're going to put in -1 for the exponent. -0.11111. So not a whole lot better there. Still kind of up there. Then let's go to 0. 0 you probably can do because 3 to the 0 is 1. Anything to the 0 is 1. That always happens first. The exponent happens first. So 3 to the 0 is 1 times -1/3 is -0.3333. So we're slightly off of that. Let's jump to 2. Okay, so we really didn't get a lot of movement there, but then we jump over to 2. So we put that in. And we've got -3. So that's reasonable. 2, -1, 2, and then I know we don't have a space or -3. But hopefully you get the idea of the shape. You can see that this was a base that was greater than 1. So automatically I think of it as going like this, like that. But it was a -a, which meant I took this thing. I'm going to erase this. You took this thing and you flipped it. A negative will flip it over the x-axis. So it actually is over here, and then it goes down. Like that. Follow me? Okay, let's do one more here. I don't know. Let's do number 4, and let's do this. -2. Let's do that. 2 to the 1/3 x minus 2. Just to throw in a little bit more variety there. So basically what you're going to be doing here, you're going to be making a chart. Not going to make it too complicated. You're going to be choosing values from left to right. Let's start with maybe -3, -1, 0, 1, 3. That's a good sampling across my chart there. And the only other thing I can do before I start plugging numbers in is I could draw my horizontal asymptote right there. Horizontal asymptote, -2. So down here, -2. Let's see, domain is our real numbers. That is going to be every single answer for that. Range, this is a positive A, so I'm going to be going up. So I'm going to be doing everything greater than -2. So y is greater than -2. Okay, after that it's just plugging in your numbers. So I'm going to give you a couple minutes here to plug in some numbers because I have a feeling some of you underappreciate the difficulty in plugging in numbers. You just copy what I have and then you get stuck when you have to try it yourself. So try that here for yourself for a couple minutes. Go through that chart Just use a regular little calculator here. You won't get a graphing one on this test. So try to plug in that stuff. Make sure you put the -2 on the end, and let's see if you fill it out the same way I do. Okay, hopefully you got something similar to that. -352, not even close to me to graph that. -1, 4. Remember, you're plotting your points from, the regular origin here. -1, 4, 0, 0, 1 there, 3 over there. So that does fit, hopefully, what we were expecting, which is, because your base right here, that's one of the b's that is a fraction. Okay, that is between 0 and 1. That reverses kind of the direction of our exponential curve. Because think about what the exponential curve did. I'll kind of give you a second here to look back here at this one. Oh, that one's not a good one. But right here, remember how we said that every previous number is multiplied by the base. Every previous number gets multiplied by the base. To go from one to the next, to go from left to right, it has to do with what the base is. So if the base is a fraction between 0 and 1, if you multiply by a fraction between 0 and 1, you get a smaller number. So when I move from left to right on this style of question, I should be getting a smaller number, and a smaller number, and a smaller number, and a smaller number. And I keep taking a third of it all the way forever. And I'm never actually going to get to, let's say, 0, in this case, -2. I'm never actually going to get there, but I'm going to keep getting closer and closer because I keep taking a third, and then another third, and then another third, and it gets smaller and smaller and smaller. Okay. That is the majority of what we have to do, but I do have to say that this is a good place to throw in this maybe a new number for you, because it's nothing special for us, but it is special in the larger sense of math, and that's what we call it's called the natural base. So we already kind of talked about what a base looks like. It's just, whatever it was, b to the x. This is the base. Okay, we already wrote that once. But when this is a special number, which we call e, okay, some numbers are so special that they get their own names, like pi. It has its own name. It's an irrational number. Same thing with e. It's an irrational number. It has its own name, and it is approximately this. Okay, it's not really. It's approximately 27 over 10, but not really. That would be 2.7, and it actually goes on and on and on. 2.71828, and it keeps going forever with no repeats. But that is a very common base. Okay, and the higher you go in math, the more e is used. So we need to introduce it because it's kind of it is, like it says, the natural base. Right there, natural base. So anyway, what you're going to see with it is this. Some number, it doesn't have to be f of x, don't let that scare you. Y equals e to the x. The thing that you need to remember, though, is that e is a number. It's just a number. It's a number in your calculator. That's really what we're going to use it for. If you saw y equals 2 to the x, you probably wouldn't be nervous about that. You'd be like, whatever, plug in some numbers in my calculator, and graph it. Well, the same thing is true if you see an e. It's nothing special. It's not a variable. It's just standing in place of 2.71828, blah, 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 blah. It's right there on your calculator. Even if you have one of these, it doesn't require a fancy calculator to have. If you look at your calculator, if you look at this guy right here, above the ln, or the ln button, is e to the x. You see it right there. So that when you have to evaluate, use a calculator to evaluate the natural exponential functions, e to the negative 2, you just plug it into your calculator. You just go to the e button. So in your case, it's what, second, and then you press ln. That gives you e to the exponent, right? Second ln. And then you just put in negative 2, and you get your answer. So what is it? Negative 2. 0.1353. 0.1353. E to the 2.5, just do the same thing. Second ln brings up e to the, then you just put in 2.5. 12.18. 12.18. Okay, so then sketching a graph, we'll just do one of these because they're nothing special. It just looks scary. Let's do letter A here, and then you can get started on the homework. Graph that. All right, so it's an exponential function because the variable is in the exponent. I don't have any k out here, plus 0, so I have a horizontal asymptote at 0. My domain is still all real numbers. My range is now y is greater than 0 because this is a positive a. It's 2. It's positive though, so it's going to go up. And the rest is now just plugging in some numbers. So I went across this way. I don't know why. I'm going to undo that. I'd rather go down. So take some x's and some y's. I don't know, good little sampling. I like my negative 3, negative 1, 0, 1, 3 method. Stretches it out a little bit. I get to see what happens right around the origin, blah, blah, blah. So let's throw those numbers in and see what you get. So you can be doing that. I'll do that. 2, and then e to the 0.24, and then up there times negative 3. So do you get 0.97? Should. Okay, as long as you're you're doing your calculation up in the exponent where you should, it should work. Okay, then wait, that was yep, that was right. Then we put a negative 1 in. $1.57. Put a 0 in. don't know how much more I'm going to get of these. 2. Put a 1, 2.54. Not really moving too fast. It's okay. And 3. 4.1. Okay, so not really shooting up yet. Just slowly going up. -3. 1, 2, 3. 0.97. -1, 1.5. 0, 2. 1, 2.5. 3, 4.1. 3, 4, let's see, I'm just going to see what 5 was just for fun. Just for fun. 6.6. It's really not going too fast. Where was that? 1, 2, 3, 1, 2, 3, 4, 5. This is 1, 2, 3, 4, 5, 6.6. So it's heading that way. Oops, I didn't do a really good job there. But going like that. So it's kind of a not quite as fast of a rise there. Because of that 0.24, it really slowed down our growth. Okay, so tonight, let me see what that looks like. I don't know. So we have a book. There it is. 402, 1 through 10. So that is, exercises 1 through 10. Evaluate the expression, round your result to 3 decimal places. So that is a calculator process. That's super easy. 21 to 36, multiples of 3. So then at 21, graph the exponential function. So 21 to 36. Yep, that's it then. 21 to 36 is all graph the exponential function. So you're doing 21, 24, 27, 30, 33, 36. So there's 6 graphs to do. You probably will need a calculator for those, but I think that's it. Very doable for sure. Okay. That's it. Ask if you have any questions. You've got a good amount of time here to finish that up. And that's it. Book is up here if you want to take a picture.